So this is the explanation video for phenomena related to reaction. Again, this was a self-study kind of thing, but then yeah, you can look at this video just to make sure you get the concepts right. And I'm going to be mentioning the important points that I need to see in your answer for full marks on the topic. So first explanation is apparent depth. Now, apparent depth is what happens. So you see this all the time when you have a piece of water. At the interface there seems to be some sort of displacement, if you will, between like the pencil. You can see that the pencil is broken over here, or like a bent pencil rather, I should say. But, looks like the pencil is bending, or weirdly shaped, and this is because of the apparent depth phenomenon. So the important thing is here, the pencil tip appears to be at a shallower depth than it really is. That is always true. So whenever you look at apparent depth, the object seems to be closer to the surface than it actually is. So the object appears, appears to be closer to the surface than it actually is. And this is because of refraction again. So we can see here that when light from this tip goes from a denser, which is water, to a rarer medium, which is R for rare, R. So denser to rarer medium bends away from the normal. So you can see that this light is bending away from the normal. And then if we extend those backwards, they appear to meet closer to the surface than the pencil actually is, because again, we think that light always travels in straight lines, and therefore when we extend this, where the object appears to be is where the light rays reaching our eyes extended backwards meet, right? So they meet at this point and not at this point, because we can't account for the bending of light. We just extend them straight backwards. Our brain just extends them straight backwards. So they always meet closer to the surface, and this is your virtual source of light. This is where you think the object is when it's actually here. So this difference here is your depth difference. So your actual depth is this. Your apparent depth is only that much. So the apparent depth is always smaller than your actual depth. Again, objects underwater always appear to be nearer to the surface than they actually are. So this is, the same idea as a pencil. The same idea as this fish. Light from traveling from water to air bends away from the normal. So if we extend those rays backwards, we arrive at a virtual object at an apparent depth, which is always closer to the surface than the actual object in depth. And this is the same reason we see shortened legs over here, because the legs appear to be closer to the surface of the water than they actually are. They're actually not that close to the surface of the water. So that was apparent depth. Next one is kind of a weird one. It's the flattened sun thing. So there's two basic, so this is like, if you look at this picture here, the sun looks kind of like, flattened at the bottom, which is not like its regular, roundish shape. It's more like someone squeezed it like that kind of, and it's become flat. And this is because of two reasons. So the first reason is that air is more dense near the Earth's surface than higher up in the atmosphere. So if you look at this diagram, you have more dense air here and less dense air here. And this is again because this is like the least dense air, because it's like empty space. So it's like a gradient kind of going. So there's more dense, and then it slowly gets less dense until, least space, or at least dense, right? Because it's empty space. So it's kind of a gradient. So like thinking about it, this kind of makes sense, right? And here, again, we observe this light that is incident along here. We look at this normal over here. So this over here, I'll zoom in. That over there is angle of incidence, or theta I. And then again, you are moving technically from a less dense medium to a more dense medium. So it's going to bend towards the normal. So the light ray is bending towards the normal. As you can see, theta R is lesser than theta I. should have continued this way, but it's bending towards the normal. Same thing over here, right? This is your actual degree. This is your theta r, which is bending towards the normal. Again, we are going to extend that backwards. Again, when we look at the sun, we're not going to account for this bending. Just like the apparent depth, we just have to extend those lines backwards like here, and we get a kind of flattened image. And the second important thing that you have to say is that the light rays from the bottom of the sun have a greater angle of incidence than the light rays of the top of the sun. So this angle of incidence here is greater than this angle of incidence here, which results in this flattened shape. Like so. Again, this one's kind of weird. I don't really like asking this one, so unless you choose to explain this, it probably won't be. I won't give it to you as a question, just because I don't like it very much. These are my favorite ones. Water on the pavement, like mirage and shimmering, so very likely to be on a test. Because the key here, it has a good amount of refraction. It has total internal reflection, and you have to learn. Sorry about the background noise. There's some kids for some reason in the atrium, and they're shouting. I don't know, but so hopefully that's not disturbing you, and you can kind of focus. But the key here is that the index of refraction of air decreases as air gets warmer. So what does that mean? Index of refraction decreases. So that means warmer air is rarer because it has a low index of refraction. Colder air is denser. So I don't know how you want to kind of think about this, but imagine cold air, it doesn't really move it very much. It's heavy, and therefore it's dense. Warm air is light, so it rises up, and so it's rarer. I don't know. That's just an experimental thing. I don't exactly know why the reason is. It's probably due to some kind of molecular theory. But all you need to know is you need to know that the cold air is denser than the warm air. So when you have pavement and there's sun, obviously, the air that is closest to the pavement is a lot hotter than the air far away from the pavement because the pavement heats up, and so the air above it heats up more. So kind of what you have at each level here, when the air gets successively, warmer and warmer, is the fact that you have this light ray that's traveling, and it's going from a denser medium, that's cold air, to a rarer medium, that is warm air. Again, I know I just said a few minutes ago that hot air rises up, but this hot air is trying to rise up, but it rises up and becomes cold over here where more air is becoming hot, because this hot air is at the bottom because of the hot pavement. So eventually this hot air will rise up, replaced with more air that is also getting hot and rising up, right? So it's a continuous cycle. So, but essentially, for the purposes of this, the hot air is considered to be closest to the pavement. We're considering that instance. So again, denser cold air, rarer hot air. From denser to rare, you're going to bend towards the normal. So you're bending so this was light ray as it was going. You're bending towards the normal as it was going. You're bending towards the normal as it was going, bending towards the normal. And you can see here that at some point, you're going to surpass your critical angle. Again, you're going from a denser to rarer medium. So first condition is check. Your second condition for total internal reflection is your theta has to be greater than the critical angle. And at some point here, you are going to satisfy that condition. You don't really have to know what that critical angle is. But as soon as you satisfy that condition, you're going to have total internal reflection. And then you're going to do the opposite. You're going to bend away from the normal. Sorry, rare to denser. Sorry, here it's towards the normal as you keep going back, but eventually it's going to reach your eyes, and you extend that ray backwards. Again, our eyes cannot process, our brain cannot process bending. It thinks light travels in straight lines. So you kind of see this virtual image over here, kind of in the distance away from the road, even though the object, which is, the sky, the object here is the sky. So what you're seeing is a reflection or a virtual image of the sky on the highway, right? Because of this. So first is denser to rarer, you're going, it's bending away from the normal until you have both conditions are satisfied for total internal reflection, after which it reflects kind of back, and then you move back from rarer to denser towards the normal until it reaches your eye. And then the last step is you extend the ray straight backwards and get virtual image of sky on pavement. Right? Okay, now the shimmering is exactly the same idea, right? So the closer you are to water, the warmer the air is, and the farther away you are, the colder the air is. So as a light ray continues traveling downward towards the warmest air layer right above the water, the speed keeps increasing as it bends away and away from the normal. Eventually, total internal reflection occurs in the lowest warm air layer. So it's basically the same idea that we showed over here, and this creates, like, the moon has you get multiple images because there's rays of light that's hitting every point, reflecting, coming back at you from every point, and so you can see different images of the moon on the water. So this is why shimmering occurs. Right? The last one we're going to talk about is a rainbow, which is kind of interesting. So there's 3 steps to a rainbow, and we're going to go through them step by step. Again, there's a kind of conditions. I forgot. Oh, they're not here. Oh, well, okay, they're the last one. So the first step is you have to have the sun behind you. So otherwise you can't see a rainbow if the sun is like in front of you, because that's just how when you rainbows involve like reflection, and therefore the image has to be the light has to come from the image is formed the same side as which the light is coming. So if the sun isn't, if you're looking at the sun, you can't see the rainbow. The sun has to be behind you, and you should be able to see the light from the sun reflected through the water droplets, and that is a rainbow. So the first step is when, we have to talk about this prism thing, where white light is split into its 7 colors going through a prism. So when you have here, because violet light, because they have different wavelengths, they kind of slow down differently, or they change their wavelength differently when they enter a prism. So violet light bends the most, or is refracted the most, whereas red light is refracted the least, right? And that's just how, because of the different wavelengths of light, they have different properties in refraction. So violet light slows down more than red light when it enters the prism. It bends more because it has a higher energy, and so violet light is refracted more than any other color. So here, what was I going to say? Yes, the first step in a rainbow is kind of your, there's 2 things that happen here. First, you have refraction, because light rays going from air into the water droplet. So refraction is going from rarer to denser towards the normal. But as this happens, you are also having, what's this called? Dispersion. There we go. Dispersion of light. Dispersion of light is splitting of white light into its 7 colors. That's what dispersion is. Splitting of white light into 7 colors is dispersion. So that's the first step, where white light enters the droplet and splits into its 7 colors. So here you kind of have the separation of the colors that you see on the rainbow. Now each of these colors, each of these different rays of light, is going to hit the back of the droplet and is going to be partially internally reflected. That means some of it does exit the droplet on the other side, is refracted, but like we said, anytime light hits a surface, some of it's reflected, some of it's reflected, right? So it's partially internally reflected, which means it's not a total internal reflection, but only a partial one. It's partially internally reflected back through the rain, and break through the drop. And when it hits here, you're going to exit the raindrop from going from water to air. And this is part of the, again, from a denser to a rarer medium is bending away from the normal. I mean, you don't really have to say any of this. So step 2 is, where was step 2? Second, partial internal reflection when it hits the back of the raindrop. Third step is the refraction as it exits the raindrop. And the light then comes into your eyes, and then you project this light through the raindrop, and because it was already split up, you can see two kind of like the red bit and the violet bit. From like the red is on top and the violet's on the bottom. Because the violet bends the most, so it's at the bottom. The red bends the least, so it's on the top. There are rainbows where these colors are flipped, so violet's on the top and red's on the bottom. They're like a double rainbow or some weird thing like that. That's a whole other thing. I don't know specifically, but they also have to do with these kinds of optical phenomena. It escapes my mind as to what or how these things work. So the last step is projecting these light ray backwards, form a virtual image of the spectrum, right? So that was a rainbow. So I would pay attention to this summary thing. These gives you kind of the main points that we talked about, and if you just want to summarize what I've said, that works too. So yeah, so that was the summary video. I'll see everybody in class.